the equilibrium will be achieved at a particular temperature. If you shift from that temperature, the equilibrium will also shift in order to absorb the effect of the change imposed on the system. So decrease in pressure favors the side with more moles, increase in pressure favors the side with lesser moles of gases. Nice to see you again here on Sir Majesty Easy World Science Channel. Today we'll take a look at a topic preparing for this forthcoming examination, and the topic is no other topic but chemical equilibrium. Chemical equilibrium. Here, you know, we deal with equilibrium in physics, and also here we are going to look at it in chemistry. And in chemical equilibrium in chemistry, it involves dynamic equilibrium because of the fact that the reaction is reversible. First, before we proceed to this topic, we need to know what we call reversible reaction. A reversible reaction is a reaction that proceeds in both directions. That is, reaction that can take forward and backward directions, whereby you can get what you garbaged in from what comes out of what you garbaged in. A reversible reaction is a reaction whereby a product can proceed to a reactant back again, a reactant that gave you the product. So to illustrate this, in a reversible reaction, if A plus B will give you on a forward direction C plus D, it shows that C plus D can also combine to give you A plus B. And this type of reaction is what we call reversible reaction. Not every reaction is actually reversible, of course. Now, for a reaction to remain reversible, it shows that it's going to happen in a slight or in a moderately closed system. What do I mean? That none of the reactants of the product will be removed, because if A plus B will combine to give you C plus D, and you remove D, leaving C, only C alone cannot form back A plus B, which means the parts, the system have to be closed to keep the reversibility constant. Now, whenever a chemical reaction is reversible, we use the term dynamic equilibrium. Then, when we say that a reversible reaction is in dynamic equilibrium, a chemical reaction that is reversible is said to be in dynamic equilibrium when the rate of forward reaction, this is forward reaction, is equal to the rate of backward reaction, such that there is no net change in the concentrations of the reactants and the product. I take it again, that a reversible reaction is said to attain dynamic equilibrium when the rate at which forward reaction proceeds is equal to the rate at which backward reaction proceeds, such that there won't be any net change in the concentrations of the species on both sides of the equation of the reaction, meaning there is no net change in the system. And remember, generally, a system is said to be in equilibrium when there is no noticeable change in the properties of that system. You say that such system is in equilibrium. Now, in chemistry, we have most reactions are reversible. And whenever reversible reaction occurs, you say it is dynamic because at a stage, the equilibrium may tend to go forward more here, but it will still readjust so that there will be a constant. So, for us to proceed, we need to look at what we call a good example of equilibrium is a saturated solution. A saturated solution, we know, is a solution that has contained the maximum number of solutes it can normally hold in the presence of undissolved at a given temperature. When you look at what I'm holding, this is saturated copper 2 tetrahydrosulfate 6 solution. When you look at the base, they are undissolved. It shows that the undissolved solute is at equilibrium with the solute that is in the solution. What I mean is that, why will it remain undissolved even when I shake it? Simple, because the rate at which the solute goes into the solution is equal to the rate at which another particle of copper 2 tetrahydrosulfate 6 is displaced out of this solution. So, a saturated solution in the presence of undissolved solute is a good example of a system that is in equilibrium. Why is it in equilibrium? It can no longer dissolve again because the rate at which, if one molecule goes into this solution, it means that one molecule of copper 2 tetrahydrosulfate 6 is displaced out of it. It's just like a seat in a church that have the maximum number, the capacity is 4 per seat. If it has taken 4, one cannot come in again. If for you to come in, you have to displace the other. So if one must keep coming in, it shows that the rate at which someone comes in should be equal to the rate that someone leaves. And when such system is in that way, we say it has attained equilibrium. Now, and remember, in dynamic equilibrium, the products of the reactants and the concentrations of the reactants and the product remain fixed, which means we need to take a look at what we call equilibrium constant. The equilibrium constant is what we're going to derive now first, before we go into the amazing principle that governs dynamic equilibrium, known as Le Chatelier's principle. But before the Le Chatelier's principle, let's take a look at equilibrium constant in a reversible reaction. So, the equilibrium constant, we will derive it gradually and now give you a way to help yourself. Let's assume we have A plus B, whereby in balancing the equation, let's assume that Y balance this plus XB forward reaction to give me, this is actually rate 1, to give me C, that is W here, plus D, that is Z here. Now, this backward, we term this rate 1. According to the law of mass action is trying to explain to us that the rate of a chemical reaction is directly proportional to the active masses of the reactants. The active masses of the reactant. Looking at this equation, A plus B is the reactant for forward reaction, whereas C plus D is the reactant for backward reaction. Taking a look at that, this means this can serve as a product and also serve as a reactant, and this can serve as a product and also serve as a reactant, depending on the direction you are considering. Now, according to the law of mass action, it shows that the rate at which A and B will combine depends on the concentrations of A and B. So the rate at which C and D combines to give you A and B depends on the active masses, that is the concentrations of C and D. So according to the law of mass action, the rate at which the forward reaction is taking place, maybe let's take it as RF, rates at which forward reaction occurs, rate at which backward reaction occurs. It will now be rate for forward reaction should be directly proportional to the active masses of the reactant, and for forward reaction the reactant is A, then by the concentration of B raised to the power the coefficients in a balanced chemical equation. Then, which means rate of forward reaction is equal to Kf. We are introducing constant to remove sign of proportionality, so that what we have here is so this is Kf. Then this is for forward reaction. If you take a look at backward reaction, the reactants are C and D. So we take it as Rb, meaning the rate of backward reaction is directly proportional to the active masses of the reactants, and the reactants here for backward reaction are the C and D raised to the power the coefficients in the balanced chemical equation, and here should be the molar concentrations of the reactants and the products. Then here should now be D raised to the power C. So introducing sign of constant, we have that, sorry, Rb, not K please. Rb now will be equal to Kb. We have removed proportionality, multiplied by this and this. Now, when do we say that this reaction is at equilibrium? It is at equilibrium when the rate at which forward is equal to the rate of backward, which means at equilibrium, at dynamic equilibrium, it shows that Rf is equal to Rb. That is, the rate at which the forward is proceeding is equal to the rate at which backward is proceeding, which means I have to equate this. I have to equate this to this. And what we have, we come down here. At equilibrium, it shows that Rf, please, that's the rate at which forward reaction is occurring, is equal to the rate at which backward reaction is occurring. That's Rf is equal to Rb. So bringing the values, what's our Rf? Our Rf is Kf raised to the power x, e raised to the power y, meaning equal to, bring our kb, or rb rather, should be constant for backward reaction, c raised to the power w multiplied by d raised to the power z. Okay, now in mathematics or in real life is situation, we will take this as a different digit, this one also as a different digit. So this is a different digit, this is another different digit. So it is obvious that 10 times 2, for example, is equal to 4 times 5. Of course, 10 times 2 is 20, 4 times 5 is still 20. Watch what I will do now. It shows that if I take this one first, 10 over 4 is equal to 10 over 4 is equal to 5 over 2. That is it, normal mathematics. So by so doing, what we have, Kf over Kb should be equal to, actually, CW all over, yes, taking this as 1. So what do we have? KF over KB should now be equal to KF over KB should be equal to C, then divide by this one. Then KF over KB is what we call K, standing for equilibrium constant. Equilibrium constant. So for a reversible reaction, the equilibrium constant is actually the product raised to power the coefficients all over the reactants raised to power the coefficient. Simple. So equilibrium constant for that reaction should be, for this reaction should be simply C raised to power the coefficient, which is W, multiplied by D raised to power the coefficient, which is Z, divided by the reactant here, which is, that is for actually taking the forward reaction first. Then A raised to power X, and what is it, B raised to power Y. So this is the equilibrium constant. See how we derive it? Because this is mathematically correct. So equilibrium constant for this particular reaction, thank you, A raised to power X, and here should be B raised to power Y, and here should be Z. So this is our equilibrium constant. Okay, having derived the equilibrium constant, one should know this. If you take, this is equilibrium constant when you consider this forward first, the reaction proceeds in this direction. But if you take this one, where here is proceeding first, you are starting here, it means that your equilibrium constant should now be just take this up here and bring this one down. You exchange it. So that's why some may tell you the equilibrium constant, when you reverse it in a way, will always give you 1. Because that's the way it should be. So remember, this is based on law of mass action, and it is proving dynamic equilibrium. Now let us take a look at 3 factors that affect the equilibrium position of a reversible reaction. Remember that a reversible reaction is said to be at equilibrium, dynamic equilibrium, when the rate at which the forward occurring is equal to the rate at which the backward is occurring. There are 3 factors that affect the rate of there are 3 factors that affect the equilibrium position of the reversible reaction. These 3 main factors are temperature, pressure, and concentration. Temperature, pressure, and concentration, as you can see there on the screen. These are the 3 main factors that affect the equilibrium position of a reversible reaction. Now, note, catalyst. Catalyst has no effect on the equilibrium position of a reversible reaction, but affects the rate at which reversible reaction attains equilibrium. Reason is this: catalyst is unbiased in catalysis. A catalyst that catalyzes forward reaction will also catalyze backward reaction in the same rate. So if it is helping forward reaction proceed to its activation energy faster, it is also helping backward reaction attain activation energy faster, which means catalyst cannot shift equilibrium position to one side. But temperature, pressure, and concentration, a change in any of these acts as a constant, and there will be tendency that when you disturb the system in equilibrium, there will be a change, of course. And remember, when there's no visible change, you say it is at equilibrium. But when you disturb it, it becomes something must surely happen. It's just like I'm holding this marker, it is straight, it is assuming to be at equilibrium because no external force and there is no change in the system. But if I apply more force here, that's taking it as more concentration here, the movement will go down the other side. So if a system is at equilibrium and you apply or you change the temperature of the system, the pressure of the system, or the concentration of the system, the equilibrium position will shift. And whose principle am I stating here indirectly? This is Le Chatelier's principle. Le Chatelier's principle states that in a reversible reaction that is at equilibrium, change in the qualities or the properties of the system, such as change in temperature, pressure, or concentration, will shift the equilibrium either to the left or to the right in order to nullify the effect of the change applied. So in a summary way, we say that if a system has attained equilibrium, a change in the property of that system will cause the equilibrium position to shift in order to nullify, to countermand, to cancel the effect of the change applied on that system. But remember that the 3 factors that when you change it, changes the equilibrium position are temperature, pressure, and concentration. Then, let's take a look at effect of temperature. Now, for you to know how temperature will affect the equilibrium position of a reversible reaction. First, you should know whether the reaction is exothermic or endothermic. Exothermic reactions are reactions that involve the evolution of heat to the surroundings such that it becomes hot to touch. Whereas endothermic reactions are reactions that absorb heat from the surrounding such that it becomes colder to touch. In other words, the internal temperature of the resulting product increases, while that of exothermic, the internal temperature reduces because it releases some of its heat to the surrounding. Now, it's a simple thing. When you bring any of your detergent, that is the linear alkyl benzene sulfonoate based detergent, and drop in your palm, then add little water, it feels hot to touch, and that's a good example of exothermic reaction. Heat is released, and in that case, it shows that the heat content of the product is less than the heat content of the reactants, because the reactants have liberated some of their heat to the surrounding, and that's why you feel it. But in endothermic reactions, heat is absorbed from the surrounding such that the heat of the product is bigger than the heat of the reactant. But to you, by your feeling, that reaction vessel feels colder to touch, because remember, like how your AC works. When you come inside your room, AC takes away heat from your room, and that's why your room is cold. But when you go outside, where it's now taking away that heat, it becomes very hot. So when a reaction feels colder to touch, it shows that the internal heat has increased, because it has taken away the surrounding heat, which made it feel colder than normal. But when a reaction is hot to touch, it shows that it has lost heat. It brought out that heat from the inside. So exothermic reaction is as a result of loss of heat. Endothermic reactions is as a result of gain of heat. Now, let's bring it to how it can affect the equilibrium position of a reversible reaction. Note this: if a reaction is exothermic, increasing the temperature will disfavor it already, because it's already hot. It's like hitting what you know is already hot. You are not helping matter. So just take it that way. Increase in temperature of a reaction that is exothermic disfavors it. So increase in temperature disfavors exothermic reaction, whereas decrease in temperature favors exothermic reactions. Now, coming to the other one, which is endothermic reaction. Endothermic reactions are favored by increasing the temperature. Increase in temperature of endothermic reaction makes the reaction faster than normal. Then decreasing the temperature makes it very, very slow. Just take it that way. Now, for you to know whether the reaction is going to be negative or positive, that is, whether the heat change is negative or positive, we need to consider what we call enthalpy. Enthalpy means the heat change of a system. So the enthalpy here is heat change is equal to heat of product minus heat of reactant. Simple. The heat of product minus heat of reactant. When delta H is equal to negative value, negative, it shows that the reaction is exothermic. This is for exothermic reactions. Exothermic reaction. Then when we come to endothermic reactions, delta H, that's change in heat, which is also equal to heat of product minus heat of reactant, will give you a positive value. That's value above 0. It shows that the reaction is endothermic and heat is absorbed. Now, for a reaction that is endothermic, increasing the temperature of endothermic reaction favors it. Increasing the temperature of exothermic reaction disfavors it. So you take a look at that. Now, let's use this to express some processes. The contact process will require the knowledge of the effect of these three factors on equilibrium position of a reversible reaction. For industrial reasons, during contact process, that is industrial production of sulfuric acid, that's your tetraoxosulfate 6 acid, you should know what will happen if you increase the temperature or lower the pressure to ensure the maximum yield of the acid and hydride of H2SO4, which is actually SO3. So this is what I'm going to write. In contact process, the major equation is sulfur 4 oxide is oxidized to sulfur 6 oxide in the presence of vanadium 5 oxide, of course. Balance the equation. Remember, they are all gases. Then here should be, okay, we need to put 2 here, and when 2 is here, 2 should be here. And this has balanced the equation. Remember, this is the major thing that happens during contact process. Let us see what will happen if the temperature of this reaction is affected when it has attained equilibrium. The heat change is negative, class, is obvious. And when heat changes are given to you in reversible reaction, it shows for the forward reaction, please. This thing is showing that the process of combination of sulfur 4 oxide, that's SO2 with oxygen, to give you SO3, that is sulfur 6 oxide, is exothermic. But the backward reaction, the breakdown of sulfur 6 oxide to give you sulfur 4 oxide and oxygen, is endothermic. In exam, the heat change given is for the forward reaction, and you should discuss it with regard to the forward reaction. Now, in this reaction, during contact process, increase in temperature of this reaction will disfavor, that's, it will shift the equilibrium. If you increase the temperature now, you are shifting the equilibrium towards the towards the left, please. This is my left hand side. Meaning, increase in temperature will favor backward reaction. Do you know why? Because if forward reaction is exothermic, backward reaction is endothermic. So increasing the temperature during contact process disfavors more yield of SO3. Remember, this is what we want. So if you want more of SO3, you don't increase the temperature so high, because the process of formation of SO3 from SO2 and O2 is exothermic. So what do? You need to lower the temperature. So lowering the temperature of this system will shift the equilibrium to the right, meaning there will be more formation of sulfur 6 oxide. Why? Because it is exothermic. So exothermic reactions are favored by lowering their temperature. Then increasing the temperature, I said again, will shift the equilibrium towards here, meaning more of SO2 and O2 will be formed from SO3. And this is not what you want during contact process. Then you are advised to keep the temperature low, but not too low for your exams. From what I explained, it means that if you lower the temperature now, that if the temperature of this system is 0 degrees Celsius, it means you have more yield of SO3. Yes, it's true, but you have more yield of SO3 at a longer time because of rates of reaction. Remember, temperature affects the rate of reaction and also affects the equilibrium position. So if you keep the temperature so low because you want to get more of SO3, it means that the rate of the reaction will be very, very slow. So you have to increase the temperature, but don't increase it so high. If scientists have discovered that the optimum temperature for this to occur is 250 degrees Celsius, as a chemical engineer or as an industrial chemist, you are advised not to exceed this temperature, because if you exceed it, you are favoring more yield of SO2 and O2, and this is not what you want. This is what you want from contact process. So, but if you take it below 250, let's assume you keep it at 100 or 50 degrees. Remember that the rate will be very, very slow. Now, this is the effect of temperature on contact process. So, in contact process, increasing the temperature disfavors the product required. That is, it causes low yield of the product required, SO3. Then you are advised to lower the temperature. Summarily, in contact process, as you see here, increasing the temperature of this system shifts the equilibrium to the right. That brings it, shift the equilibrium to the left hand side. This is my left, of course. This is it, leading to more yield of SO2 and O2. But lowering the temperature shifts the equilibrium to the right, leading to more yield of SO3. Remember, this is what will be dissolved in water, though it is highly exothermic, to give you now H2SO4. So what we want is SO3 and not SO2. Now, that is it for effect of temperature. I'll give you another one. In industry, we have Haber process. Haber process. Haber process is the industrial process applied in the production of ammonia, and it involves the direct combination of nitrogen gas and hydrogen gas to give you ammonia gas. So here, balance the equation. There should be 2 here, 3 here, and that makes the equation balanced. Here is gas, all in gaseous state. And of course, just like this, the heat change is still negative. And what does it mean? It means that the reaction is exothermic. Now, in Haber process, remember this is contact process. And here is Haber process. According to Chatelier, that's his theory in 1888, that's Henry Louis Chatelier, he's trying to tell us that when the rate at which nitrogen and hydrogen combines to give you ammonia, when it is equal to the rate at which ammonia breaks down to give you nitrogen and hydrogen, you say they are at equilibrium. But let's assume the temperature is affected. The equilibrium will be achieved at a particular temperature. If you shift from that temperature, the equilibrium will also shift. If you change the temperature at which these have attained equilibrium, the equilibrium will shift either forward or backward, either right or left, in order to absorb the effect of the change imposed on the system. For you to get more ammonia class, you need to lower the temperature of this system. Do you know why? Because forward reaction is exothermic. Then for you to get more nitrogen and hydrogen from ammonia, you need to increase the temperature. Why? Because the reaction is purely, the backward reaction is endothermic. Remember, if forward is exo, backward is endothermic. So during Haber process and contact process, you are advised to keep the temperature moderate on the prescribed level. I think 250 degrees Celsius is the ideal or the optimum temperature during Haber process. Going above this, going up to 500 degrees Celsius, shows that you are going to disencourage more yield of ammonia. That is it for the effect of temperature. We now come to the effect of pressure. What is the effect of pressure change on the equilibrium position of a reversible reaction? For you to know the effect of pressure on the equilibrium position, you have to consider two factors. Two factors must be obeyed, not when one is obeyed and the other is not obeyed. They work simultaneously. They have a kind of cumulative effect, whereby if A is correct, if condition A is correct and condition B is not correct, it shows not correct general. But two of them must be correct. So what are the two conditions that must be met before pressure will have effect on the equilibrium position of a reversible reaction? Number one, at least one of the reactants or the product will be in gaseous state. That is, we must have a gas either in the product side or in the reactant side. In a situation whereby the whole reactant and the whole product is in solid, liquid, or aqueous, pressure changes will have no effect on the equilibrium position of such reversible reaction. Now, second condition is that the number of moles of gases must not be equal. The number of moles of gases must not be equal on both sides of the reaction, meaning the number of moles of gases on the reactant side will not be equal to the number of moles of gases on the product side. Remember, we are considering gases only. We are not calculating for the number of moles of solid, liquid, or aqueous species in an equation. So, these two conditions must be met before pressure will have effect on the equilibrium position. To explain this, when we explain temperature, we say exothermic, endothermic. This time around, for you to know the effect of pressure, you must know the state of matter. Let's use, for example, in the laboratory preparation of hydrogen gas by passing of steam over red hot iron is a reversible reaction, of course, to give you diiron 3 iron 2 oxide plus hydrogen gas. This is a gas, this is steam, which is gas. So balancing the equation, you need to put 3 here. Because of the 4 here, that should be 4. This is solid, of course. Then this is solid, and 4 should be here. That makes the equation balanced. Watch this. Definitely, we need to, this reaction is purely, it's an endothermic reaction, of course. It's endothermic. Change in heat should be plus. So temperature, if you increase the temperature of this, there will be more yield of hydrogen gas. Then, what about pressure changes? For you to know the effect of pressure, you must check if there is gas. Yes, one, here is gas. There is also a gas. Remember, if there is only one gas here and there is no gas here, pressure will still have effect. What we say is that there will be one gas in either the reactant or the product. Not that there will be one gas one side and one gas the other side. If all our gas is fine, then condition 1 is met. At least we can see a gas in the reaction. Then condition 2 says that the number of moles of gases on both sides must not be equal. We are looking at if pressure will have effect. If pressure changes will have effect on the equilibrium position of this reaction. Look up here. Here we have 4 moles of gas. Here we have 4 moles, which means pressure will have no effect. Pressure changes will have no effect on the equilibrium position of this reversible reaction. Why? Because there are equal number of what? Moles of gases on both sides. The number of moles of gases must not be equal. Okay, we take another step. Coming to contact process. Yes, calculate the number of moles of gases. Here is gas. We have all of them are gases. So here we have, for the reactant side, we have 2 plus 1, which gives me 3 moles. Then how many are here? 2 moles. Yes, it shows that pressure changes will affect the equilibrium position of this reversible reaction. Why? Because we have gas. In fact, all of them are gases. Then here, there are unequal number. This side 3, this side 2. So pressure will have effect. Now, increase in pressure of this system. Shift the equilibrium to the right. Simple. If you increase the pressure, you favor the side with lesser mole. If you increase the pressure, you favor the side with lesser mole. Which means during contact process, the pressure of the system needs to be increased to the highest level that the production plant can hold in order to have more yield of SO3. What I mean is that increase in pressure of this will lead to more yield of SO3. In other words, shift the equilibrium position to the right. Why? Because there are lesser number of moles of gases on that side. Which means if you want to favor more SO2 formation and O2 formation from SO3, you need to lower the pressure. So decrease in pressure favors the side with more moles, increase in pressure favors the side with lesser moles of gases. Then bring this to Haber process, that is in the production of ammonia gas. What will happen to pressure change? If the pressure of this system is increased, let's go. How many moles of gases are here? 1 plus these 3. So we have total of 4 moles. Here we have only but 2 moles. And this is gas, this is gas. So the 2 conditions are met. So increasing the pressure of this automatically shifts the equilibrium to the right, just like you did in contact process. Which means during Haber process, you need to increase the pressure of the reacting system. Very high. The only limiting factor you have is the ability of the reaction vessel, because remember, increasing pressure so high might lead to explosion. But just know that the higher the pressure during this process, the more you have your ammonia. So to keep this going, you have to keep removing the ammonia as they are formed to force the equilibrium to take that right side. Increase in pressure, shift the equilibrium to the right, meaning favors forward reaction, then disfavoring backward reaction. Lowering the pressure of this system will disfavor forward reaction and favor backward reaction. So these are the conditions that must be met for pressure to have effect on the equilibrium position of a reversible reaction. The last one is concentration. Concentration is very, very simple. When you garbage in more, you get more. Simple. If you cook 5 cups of rice, you get more plates than someone that cooked 2 cups of rice. So if you need more ammonia, if you need more of these products, add more of this, which means increase the concentration of the reactant if you need more of this product. So increasing the concentration of nitrogen gas and hydrogen gas will shift the equilibrium to the right. There will be more yield of ammonia than this. Then if you increase the concentration of ammonia far more than nitrogen gas and hydrogen gas, there will be more yield of nitrogen and hydrogen. So the equilibrium shifts to the left. You favor the backward reaction. That's the effect of concentration. Which means in concentration, I still use my marker. If I want more of this end, I will increase the concentration of this end. Since I know that from this end I go here. If there are more particles here colliding, I'll have more of my products here. So if you increase the concentration of this, if you turn it down here, you see that there will be more yield of this. So if you increase the concentration of product, there will be more yield of reactant. If you increase the concentration of reactants, there will be more yield of product. So this is it for chemical equilibrium. Remember all I've said so far. A reversible reaction is a reaction that proceeds in both directions, such that the products can give back the reactant. Then a reversible reaction is said to be in dynamic equilibrium when the rate of forward reaction is equal to the rate of backward reaction, such that there is no net change in the concentrations of the reactants and the product. Then we consider equilibrium constant, telling you that simply the equilibrium constant of a reversible reaction is equal to the concentrations of the products raised to the power of the coefficients in a balanced chemical equation all over the concentrations of the reactants, depending on how. And I derived the equilibrium constant mathematically according to the law of mass action. Then I give you Le Chatelier's principle, that was stated by Henry Louis Le Chatelier, a French chemist, of course, telling us what will happen if we change some factors of a system that have attained dynamic equilibrium. That the equilibrium will shift in order to cancel, annul, or countermand the effect of the change applied. So changing the temperature of a reversible reaction is automatically changing the equilibrium position. In other words, there are 3 constants. There are 3 constants to any system that is in equilibrium, that is, to a chemical equilibrium. Any chemical reaction, reversible reaction that is in chemical equilibrium, if you change the temperature, pressure, and concentration, you have affected the position of the equilibrium. And remember, I also told you that catalyst has no effect on the equilibrium position of a reversible reaction. The property of a reversible reaction that catalyst affect is the rate at which it is proceeding. Why? Catalyst is unbiased in action. Catalyst that favors forward reaction also favors backward reaction. Thanks a lot for being there. Don't forget to book for your private classes. I will help you out as far as sciences are concerned. And remember, the name of the channel is Easy World of Science. I make things easy for you. Don't forget to subscribe. Share my videos. God bless you for visiting Sa Majesty. See you next time.
You are Alpha and Omega.